Hello YouTube. Today we're going to be talking about small sample confidence intervals when you're trying to calculate your mean for a population, and we're going to use something called the t-distribution. Now the key thing I want to emphasize for this video is that we're dealing with small samples. It really changes your statistics analysis drastically when knowing you have a small sample versus a large sample. Now determining what is relatively small and relatively large is up to the decisions of the researcher, or depending on the type of research you are conducting. But you could say something small could be something 30 or less, or you could say something small could be, no, that's too big, we should maybe make it 15 or less. No, that's way too small. We have to consider something that's at least 50. So it really depends on what you determine to be small. If you remember in the last video I had dealing with large sample sizes, if we had a large sample size, as our sample size continued to increase in numbers, so if we had more and more people or things we were collecting in our sample, according to the central limit theorem, which we talked about, you would get closer and closer to a normal distribution. So if you have 1,000 and then you keep getting to 2,000 samples, you will have more and more, you will get closer and closer to a normal distribution. Now, for a small sample, we actually have to make an assumption that we're dealing with a normal distribution as well. And although it is a dangerous assumption to make, and it is a bad one kind of too, but we have to do this because if you have time constraints or resource constraints, and you need to have a small sample for those reasons, you need to perform statistical analysis, and to do that you will have to assume a normal distribution, and the t-distribution method allows us to account for that as well. So let's jump into the t-distribution. This is going to be a brief overview. It might not make too much sense at first, but one thing to know about the t-distribution is that it is mound-shaped and symmetric, just like the normal distribution. There are a lot of mound-shaped and symmetric distributions. We just talked about the normal one earlier, and now we're talking about the t-distribution. Now what that looks like, the t-distribution is at the tails, it's above the normal distribution, but the normal distribution has a higher mound-shaped or peak. So that's how it looks relatively, a rough sketch of those two. Now when talking about the confidence intervals, which I had in the previous video, you would take the mean of the sample plus or minus your t alpha over 2 times your standard error, which is your standard deviation of the sample over your sample size. Now the difference between a normal distribution and a t-distribution is simply the t alpha over 2. For a normal distribution you would use z alpha over 2. Now what that means, another thing we have to talk about before I get into that, is degrees of freedom. I'll abbreviate that as df, and that is simply your sample size minus 1. Now degrees of freedom are used to determine the shape of the t-distribution graph, which accounts for that shape in green. So this is why it differs in terms of how visually they compare to one another. So now I'm just going to get into an example to hopefully explain how this really operates, or how you would work with this with a small sample. So notice how you have a sample size of 4. That is a small sample, we're going to say. It definitely is a small sample. And it is the average of the sample is 32.81, and the standard deviation of the sample is 2.48. Now you could, I think this is numbers I got from the areas of the wings span or something of monarch butterflies in a given area, so that's what it would come out to be. Now if we wanted to calculate the 90% confidence interval, alpha is pretty much, remember, the percent that we are not confident about, so that'd be 10%, since we're 90% confident in this interval, and alpha over 2 is simply half that, which would be 0.05. And then we have to see our t-distribution table, and I'll get into what that looks like in a second, but you would write that as t alpha over 2. Now you would look at this table. This is a table. Now the key thing to note is the graph at the top does show the picture that we are dealing with that tail end of the shaded region, and in the z graph, or the z table, these values in the middle were actually areas under the curve, but in this case they're actually not areas, they're actually the t values themselves. And if you notice the column on the left, these are your degrees of freedom, and then this is your probability, or your areas are listed above. So it's kind of inverted compared to the normal one that you're probably been used to both using z-tables. So since our degrees of freedom, since we have a sample size of 14, oops, that's what I meant to write. Yeah, that 4 would have been way too small of a sample size. So 14, to make this better, I guess, so we'll use a small sample size of 14. So our degrees of freedom is simply 14 minus 1, which would be 13. And we are looking for a 90% confidence interval, so that means we'd have 5% on the tail, or excuse me, yes, that's correct, 5% on each end. So you have 5% over here and 5% over here. So then you would have 5% on each end, which would give you a t-value of 1.771. So now you put that value in, and remember this is degree of freedom with 13, and you get that value 1.771. You use the formula and you simply plug your mean in that you were given, and you do plus or minus your t value, which you got from the chart, and then use your standard error, which is your sample over your sample standard deviation over your sample size, and then you get your value of 32.81 plus or minus 1.17. Now that's your confidence interval. You say, I am 90% confident that the actual mean of the population lies plus or minus 1.17 from 32.81, and you can convert this to an interval notation as well. So now let's manipulate a few things to really get an understanding if that wasn't clear. So we're going to do a 95% confidence interval with the small sample. We'll do the same numbers, n is 14, standard deviation, same, everything's the same, except we're just switching the percent confidence. So now our alpha instead of being is what we're not, our alpha is what we're not confident about, and that's 5% of the date of the interval. So alpha over 2 would be half that, which is 0.025. That means now we have to look at our t-value, and our t-value with a degree of freedom of 13, we'd have to look, so we're back here again, but now we're doing 0.25 of that, or 0.025 of that. So we have our degree of freedom, and then we look at our 0.025, and we get, I think that's right above it. So our value would be 2.16. There it is. Okay, so 2.16 would be our t-value. So now that we have that, we use our 2.16 for our t-value and plug in the formula. Remember that was given, plus or minus our t-value times the standard error, and you would get your confidence interval. Now notice what happened between our confidence interval here and our confidence interval here. What's different is that our interval has expanded if we increase the percent of confidence. And you can think about this as having a bigger net to capture in their sample population. Say you're trying to get a population of fish, and you wanted to take a sample. If you wanted to be 95% confidence that their weight lied between here, you would want a bigger net, I guess you could say, for the analogy, is your confidence interval. So this portion changed, or the plus or minus 1.43 is larger. So now, what if we changed our sample size to be 20, which we're still considering to be a small sample? So this would imply that our degree of freedom would be 19, since it's n minus 1. So now if we have to look at our t-value for 0.05, and that I kind of gave it away, but would be 1.729. So now we look at 19, and then you could pull the 1.729 value by looking at 0.05, because that's what our, we're still going to talk about our 95% confidence. So then you get that 1.729 value. And then you simply use the formula again. Our mean has stayed the same, and we just altered our sample size, but that has impacted the t-value, if you notice. Instead of being 2.16, we're now at 1.729. And it also has changed our standard error. So it has two impacts here, which made actually our interval to decrease. Notice it's smaller. We're having a 0.96 compared to 1.43. So that means if we increase our sample size, this affects both the standard error and our t-values, so our interval decreases. So that's how you could say how n affects our t-distribution and our percent confidence interval as well. So let's analyze this table. A few things I want to point out. As n increases, our degrees of freedom increases. So obviously if you have, notice how we went from 14 to 14 sample size to 20 sample size, our degrees of freedom increased as well, but it's still smaller because it's n minus 1. But our t alpha over 2, our t value, decreases really, really fast. Now, to think about that, if we look at this table, if you pick any column and you look at the values, you'll notice that at the top, these numbers are really, 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 really big. But let's just look at one column. Let's just look at the 0.05 here. So notice as your degree of freedom is really small, your t-value is really large, and that, remember, was written in, I wrote green here, so that value gets really, really large, so that really increases your interval. So, but as we go down, notice how these numbers are getting smaller, smaller, and smaller, and that's as your degrees of freedom get larger, larger, and larger. But if you notice, there's a kind of pattern to it, so it's really big change at the beginning, but then slowly and slowly they're making smaller and smaller changes or increments. Like down here, 1.664 goes to 1. It has a difference of 0.004, and then there's another 0.004, and you notice how that pattern slowly gets smaller and smaller, but it's approaching something. And as you approach infinity, you get to a number that is actually what our z value would be for your normal distribution, which is really cool, because you're actually, as you get larger and larger degrees of freedom, which means you have a larger and larger sample size, you are even closer to the normal distribution. So even this t-chart does kind of hint at the central limit theorem that we talked about at the beginning of this video. So that's just kind of how you can notice a few things about the chart to get a better understanding. So again, to make it in mathematical terms, as the limit as our degrees of freedom, I'm kind of saying, went to infinity, that means your t values would approach the values of the z table. So you can use that as well. And one thing I want to touch on is defining large. So if we say that for a sample large, I think is 50, then everything less than that would be small. But it really depends on the person doing the research and the type of research you are doing. I kind of talked about that at the beginning of the video. So here are some conditions when using t-distribution. Your data must be viewed as if it were generated from random samples, so you have to make it seem that it's not all skewed towards one side or another. It has to be randomly generated, or appear to be. And the population must be 95% larger than the sample size. This is kind of saying, if you use t-distribution, empirical analysis tells us that if your sample size is larger than 5% of the actual population, then pretty much you can't use t-distribution. It just statistically it doesn't make sense to the actual results, and this is only true just because the data has shown it. There's like, if you do this test over and over again, if you take half the sample size of the entire population that you know, t-distribution will not give you accurate results. It only works, again, for small samples. This is why we use it. So another thing to note is that observations are independent from one another, so there's no one, like, you are not more likely to choose this this individual sample versus another individual from the same sample. So it's equal choice of being chosen kind of thing. There's no influence. So then finally, we have, if our sample size is small, then we assume that the distribution is approximately normal. So we need to do this to make sure our data about the population, it's a kind of cycle kind of argument where we have to make an assumption, which is usually not really good to make, especially for small samples, because you might not believe that that actually represents the population. But we need to do that in order to gain some sort of evidence and statistical analysis about the population as a whole if we don't know much about it. So this is what's interesting about statistics, is instead of plugging and chugging, which it might seem like you're doing at first, when you're doing this sort of mathematics, but it's more about the analysis, which I think is really keen to have, analyzing what that plus or minus means in terms of your range of how close you are. You are 90 to 95% depending on your confidence interval, to choosing the mean of the population, of the actual population, to be in between that range. So it's about the analysis. So having a deep understanding of what these numbers actually mean is probably the most you can probably get out of a statistics class, is that intuition and analysis. That meant not honestly many people don't really have access to that kind of education when it comes to trying to have that analysis. So yay for the internet to being able to access stuff like this. But gaining that practice and experience by looking at the numbers and seeing what they mean and figuring out why you're using these formulas, and understand where those concepts come from, it can give you a better understanding and more of an analytic kind of mindset when you are going through your career later in life. So hope this helped. Again, compare these tables. You can look at the Z table. I think I have it here. I should have brought it up earlier. But again, these were areas on the inside, and their Z values were determined on the side. But now our T table, the areas are on the sides and the degrees of freedom are on the sides, and rather the T values are in the middle.